Well, there was a film a few years ago with Russell Crowe starring as John Nash. It was called A Beautiful Mind. There's also a book, A Beautiful Mind, that it was based on by Sylvia Nazar. I enjoyed the book more than the film. The film's a little bit fictionalised, but it's a good portrayal of his life story. You may have heard of him because of his work in economics. He won a Nobel Prize for economics, and that was for game theory. So he analysed what are called non-zero-sum games. And that was a big deal back in the 1950s when people were worried about nuclear conflict. He used a topological theorem, the Brouwer fixed point theorem, to prove the existence of something called a Nash equilibrium in a game. For a pure mathematician, that was quite a simple application of those things, but the really big deal was that he brought those mathematical ideas into economics. But he's really well known among mathematicians as well for some serious pure math work that he did in a subject called differential geometry. Well, the mathematician Mikhail Gromov said that he thought that Nash's work in differential geometry and on elliptic partial differential equations was orders of magnitude more important than his work in game theory. But of course that's the point of view of a pure mathematician. So I'd like to talk about something that's not so well known, which is the Nash embedding theorem. So it's about how can you realise abstract curved spaces as subsets of Euclidean space, the space that we live in. We can think first about a torus. So I've got a bicycle in a tube here. This wasn't out of my bike, it's actually a fresh one because the previous one burst. This is a donut shape, if you like. You can imagine the surface is quite squidgy. It's the same shape as the surface of a donut, so topologically it's equivalent. But we can imagine that it's pretty stretchy. It's got some distances already marked out on it. So there's a grid marked out on it. And we can imagine that you can already measure the distance between 2 points on the surface by tracing along this grid and seeing how many squares you go along. So we can imagine a stretchy surface, but it's got its own intrinsic idea of what the distance is. If I twist it here, you can see the rectangles are getting to be longer and thinner. If I twist it the other way, they get long and thin the other way. So what Nash was interested in was, given one of these surfaces, with an idea of distance already marked on it, can we find a way to put it in three-dimensional space in such a way that the distances agree with the distance traced around the surface in three-dimensional space? So if I have a curved surface in three-dimensional space, it's already equipped with a distance, which is just the distance, let's say, between 2 points. I can trace lots of different curves on the surface, and I'll just take the shortest one of those, and that gives me a notion of distance. And that's called a Riemannian metric on the surface. But you can also have an abstract surface, which is equipped already with a Riemannian metric. And then we want to know, does it come from an embedding? Does it come from a way that you can put the surface into three-dimensional space? Just to talk about what embedding is, this is an object that you might be familiar with. It's an attempt at making an embedding of a Klein bottle. So the Klein bottle is a surface, it's a closed surface. It's actually just got one side. So if you imagine going around through the tunnel, then you'd be on the inside of this tunnel, and so you've got through to the inside of the bottle then. So it's a rather unusual surface, and it's got no boundary, but there's a problem with this glass one, which is forced on it by being in three-dimensional space, which is that it intersects itself. You can see this tube here is passing through a piece of the surface here, and what we'd like actually is to realise the surface in, let's say, four-dimensional space in such a way that there's no intersection with itself. This is what's called an immersion. So it's everywhere it's smooth, nicely curved, but it intersects itself.
So that's kind of like a flaw. That means it's not a real Klein bottle.
That's a flaw. So this isn't really a Klein bottle. We'd need to go into 4 dimensions to have a properly embedded Klein bottle. So embedding means that any 2 different points on this abstract surface have to be placed at different points in space. It turns out that it's actually impossible to embed a Klein bottle in 3-dimensional space.
Oh,
you can't do it.
That's where the failure is.
That's right. No matter how you try to fit it into 3-dimensional space, there are always going to be 2 different points on the Klein bottle on this abstract surface which have to be at the same place. So here we've got something else. If we cut a bit out of the Klein bottle, we end up with something called a Mobius band or a Mobius strip. And you've probably seen one of these before. So I just took a long rectangle of paper and I gave it a half twist and I sellotaped the ends together. This is getting a bit closer to what Nash proved because it's made of paper, and paper already knows what the distance is between any 2 points. When you curve paper, it only likes to curve in one direction. It's always straight in the other direction. So it's bent this way and it's straight this way. And you can't bend it so that it looks like a piece of a sphere. Paper doesn't like to bend that way. So any way that we embed this Mobius band made of paper into three-dimensional space, it's always going to be isometric. So isometric is exactly the property that the distances on the paper are the ones that you would get from finding the shortest path along the surface in three-dimensional space. Whereas with the inner tube, I could imagine if I have just a sort of square grid going around it and going in meridians and longitudes around this torus, then going around the inside, I'm going to get a slightly shorter distance than if I go around the outside. There's a natural metric on a torus called a flat torus, where it's difficult to embed it in a smooth way into three-dimensional space. But Nash proved that if you were allowed to embed it in a slightly irregular way, then you could even embed the flat torus, so that particular distance structure on the torus, into three-dimensional space. So the flat torus is the one that I could get from a piece of paper if I started with a rectangle and I bent it round into a cylinder and glued it together, and then tried to bend it round so the two ends of the cylinder were glued together. And you just can't do that with paper. Paper doesn't like to be embedded in that way in space. Whereas I've got this torus made of rubber, that's easy to do because it's bendy. Now Nash showed that actually if you fold, well, folding is not quite right. So folding is not allowed. You've got to have a direction at every point in his embedding. So with the rubber tube, there's this valve sticking out of it at right angles from the surface. You could imagine that on this Mobius strip that you could also have little sticks pointing out at right angles from the surface everywhere. Those are called normal vectors. Nash's condition was that he wanted the normal vectors to vary continuously as you move around the surface. So if I make a fold, then the normal vector, here it's sticking out this way, and then as you go around the corner, suddenly it flips to being over here. So that's not allowed. You're not allowed to fold. So Nash was interested in embedding this flat torus made of paper so that everywhere you embed it, the normal vector exists and it moves continuously. And he showed that actually you can do that, which is quite a counterintuitive result. The catch is that the normal vector moves continuously but not differentiably. So if you know what that means. So it's a bit like a fractal embedding. In fact, it was any Riemannian manifold. So it doesn't even have to be a surface. It could be three-dimensional or four-dimensional. You just have a manifold, so it's a curved space, if you like an abstract space, which you imagine as being made of rubber, and you're trying to embed it in Euclidean space, but maybe 10-dimensional or 20-dimensional Euclidean space. So we've got, let's say, a 5-dimensional, if you can imagine 5-dimensional rubber. We've got this 5-dimensional object. Let's say it's like this torus. There's no boundary, and it's just a finite bounded thing. Mathematicians call that compact. He showed that if you have an m-dimensional manifold, so a Riemannian manifold, that means one of these curved spaces with the distance already prescribed on it, it can be embedded isometrically. So that means that the distance is exactly the one that you get from the Euclidean space.
You preserve its grid.
That's right. Now how many dimensions do we need? We need m times 3m plus 11 over 2. That's a lot of dimensions. There's an extra condition about the type of the embedding. So how regular is it? Can you take the coordinate functions and differentiate them lots of times? For this theorem, with this many dimensions, this embedding can be as smooth as you possibly could imagine. So the technical thing for that is C infinity. It means you can differentiate all the coordinate functions as many times as you like. So for the tire, we've got m equals 2. It's a surface, so it's got 2 dimensions. at any point on the tyre you can go in 2 different directions at right angles. And so if we plug 2 in here, what are we going to get? 3 times 2 plus 11, that's 17, times 2 divided by 2. So we need 17 dimensions. 17-dimensional Euclidean space. That's hard to imagine, but Nash's theorem says that no matter what structure you have on the surface to start with the distances, as long as they're suitably smooth, so suitably differentiable, then you can embed it in 17-dimensional space in such a way that you recover the distance from the embedding.
But does it have to be that high?
It doesn't necessarily have to be that high. That's what he proved you could do for any possible distance that you put on the surface. So this is an upper bound on the number of dimensions that you need. So in the case of a torus, it may be that 3 dimensions is enough, and it may not be that 3 dimensions is enough. So in particular, if you want to embed the flat torus, so that's the one that you get from taking a rectangle of paper and gluing the opposite sides, if you want to embed that even so that you can differentiate the coordinate functions twice, so just a little bit smooth, then you can't embed it in 3-dimensional space. And that's because there's always going to be a point somewhere on the extreme of the torus where the surface is curving in the same way in both directions. So like a little piece of the sphere. And the curvature of the surface is something that the surface knows about. So just from knowing the distances on the surface between 2 points, I can tell you what the curvature is there. And so a point of positive curvature, so that means like a sphere, that's not going to be the same as a flat torus. Well, before he came along, there was a question about whether surfaces that you get in as subsurfaces of high-dimensional spaces are really just the same category of objects as these abstract surfaces with Riemannian metrics on them. And so he answered that. But also the techniques that he used were very important. So his proof was solving a system of differential equations called partial differential equations. And he actually did a lot of important work in proving the existence of solutions and also the regularity of the solutions. So can you differentiate the solutions? He proved that in many physical situations where you have a partial differential equation which is called elliptic, so that's a particular condition that comes up a lot in physics, for example, then the solutions are actually analytic. And that was one of Hilbert's problems. If you know about Hilbert's list of problems at the beginning of the 20th century, that was Hilbert's 19th problem. Of course, his life story is interesting to all of us because of his mental illness and the remarkable fact that he recovered from it to become an active mathematician again. But really his mathematics is what's going to last.
I've got something I can use. Oh, what about that? We have the torus shape, and for my next trick, here's a poodle. So there's our torus shape, and that's what the shape we want to make. So if you were playing the game of asteroids, this is actually the universe that you're living on. You're actually living on the surface of this universe.